This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Our speaker is Matt Papakipos from Google. He was the founder of PeakStream, which was acquired by Google this year. Actually, since we invited Matt to come and talk in this classroom, because I knew about PeakStream and thought it would be very interesting as a good talk for this group. That was probably in April or May, back in the spring. After that, they got acquired by Google. So there was even some question as to if, can he still come and give a talk? Can he talk about as much? But we were able to get everything cleared for him to give a talk about PeakStream in detail, even though they've been acquired by Google. Let me give you a little bit of background information about Matt. He has a bachelor's degree in science or a bachelor's of science in mathematics and computer science from Brown University. He ran the GPU architecture group at NVIDIA for a long time, including both the TNT products, GeForce, and Xbox. Then he was the founder and CTO of PeakStream. And recently, was it this summer? May. In May, okay. So in May, they were acquired by Google. PeakStream was founded in 2005 and acquired by Google in 2007. Their product is a software platform for programming multi-core processors. And he's going to describe for you today kind of, what does multi-core mean, and then how does their technology map to multi-core. And this includes both CPUs and GPUs. And PeakStream's technology included system development tools, including pretty sophisticated debuggers and profilers. This is just a quick outline of the talk. This kind of information is also included on the class website. However, we'll try to review it each week just briefly in case people haven't all read the class website before class. Especially for the first week, I don't expect you to have done so. So the company history will be covered from the early Stanford connections. Pat Hanrahan was part of the initial team at PeakStream. How many people here are in Pat's group doing research? Okay. So if you're interested in that, talk to him afterwards too. And it will cover from the founding to the product and its technology all the way to the Google acquisition in May this year. He'll talk about the challenges and how do you program Manycore processors, application areas that can take advantage of the performance that these chips offer, and the PeakStream software architecture design choices and the challenges they had in implementing the architecture and solutions they came up with along the way. He'll also cover the developer's programming model and the underlying software technology. And there's going to be information in the slides about sample applications, including code examples, and how do they work in the PeakStream software, and how the PeakStream virtual machine can make this all work for different hardware targets. And then at the end, he's also going to talk to you about kind of his projections for the future of where multi-core is going, what Manycore processor hardware and software will look like going forward. So please welcome Matt Papakipos from PeakStream and Google.
How do I turn this on? Am I on now?
Yeah, it should be on. There's two switches.
Is the mic working? If I don't see you and you want to make a comment or ask a question, and I will be around afterwards to answer questions or chat about anything that interests you here. So I'll try to spin this talk. I've given this talk a couple times before. The slides here are all up on the web. So if there's anything you want to look at in detail, just bring them up at your leisure. I'm going to move through it fairly quickly. Not working? Oops, that's in the off position.
Yeah, let's try that. There you go.
That looks a little better. Okay, so I'll move through it relatively quickly, and feel free to ask if you have questions. I'll try to spin this talk a little bit more about sort of how you go from an idea and a problem that people are having into a company. So I'll talk a little bit about how we came up with the software architecture as a solution to some problems that people were having in the world and some trends in processors. So PeakStream was a startup company founded in February of 2005. At our peak when we were acquired by Google, we were 35 people, so a relatively early stage company, only 2 years old. Our mission statement was to provide a software platform for high-performance computing that unlocks the power of this new generation of processors, including CPUs and GPUs. So I'll talk a bit about what I mean by high-performance computing and what this class of processors is. So who was the team? The team was myself, Matt Papakipos. So I have a background in computer graphics and computer architecture at NVIDIA, and started my career programming weird machines like the connection machine, which I've always had a certain fondness for. And you'll see some reflections of that in this company and in the software architecture we created. Pat Hanrahan was one of our Stanford connections. Pat is a professor in the graphics department upstairs and led the Brook project, which in many ways is the inspiration here. So I'll talk about that a bit. And then the two chief software architects were Brian Grant and Chris Demetriou, who are both now at Google as well. Brian brought a lot of compiler background from Transmeta, did the code morphing software there that made Transmeta's microprocessor work. And Chris Demetriou is systems architect. There was a lot of systems level problems we had to tackle that I'll talk about in the talk. So Google was acquired by Google acquired PeakStream in May of 2007. Existing product line sales were discontinued. It was really acquired for internal use at Google. So PeakStream's future is really part of Google. So I'm in the strange position about talking about a company that no longer exists. So there's not a tremendous amount I can say about Google here. So really I'm going to focus the talk on what PeakStream created, what the market need was, and what we were selling when we did exist as an independent company. So there we go. So so before PeakStream, so let me set the stage first. So I promised I'd talk a bit about sort of why we created this. So what did the world look like before we started the company? The world looked intriguing. So we were seeing press about GPUs having a whole lot of flops, meaning floating point operations per second. So being very fast at floating point calculations, 10 times faster than CPUs is what the press said when you look at peak flops. Stanford had demonstrated this Brook project, and I'll talk a bit about what Brook was, but it created a lot of buzz. So there are all these articles in game publications on the web and high-performance computing publications speculating about whether GPUs could be used for computation, not just for graphics, but for normal computation stuff. So what was Brook? Brook was a Stanford research project done in the graphics lab upstairs. Pat Hanrahan, Kayvon Fadahalian here in the audience, many other students contributed to this. And it was a very interesting project where they used the graphics processor and created a compiler for it that would allow it to run high-performance computing codes. So take this graphics chip with a set of graphics APIs made for doing OpenGL and Direct3D and make it do high-performance scientific computing calculation. So I'll talk a bit about what I mean by that kind of workload. Brook is an open source project today. Not terribly active today, but it made a big impact when it came out in changing how we thought about what GPUs could do. I think today, looking back at the history here, we sort of see this wider class of many-core processors. So GPUs were one of the first here, but not the only, and in fact, not the earliest even. So there's GPUs today sold by AMD and NVIDIA, clearly are these sort of many-core, up to 128 processors per chip. IBM Cell Processors has come out now as the heart of PlayStation 3, right? This is this 9-core, very large chip for doing gaming. But Intel and AMD have also stated their direction that they're moving towards dramatically more cores, not just sort of 2 and 4 cores, but way more cores, 12 and 16 and 32. And then we're starting to see the processor vendors talk about hybrid architectures, like the AMD Fusion processor, which is sort of half GPU and half CPU. So I'll talk more about this at the end of the talk, but this is sort of where the hardware landscape has been going. So the characteristics of these processors are very high memory bandwidth, extremely high flop rates, so a lot of floating point units, and then nonetheless a very high floating point to memory access ratio. So I'll talk a bit more in future slides about what that means for software. And then some sort of on-chip communication network. So a lot of cores on the chip and some ability for those cores to talk to each other. So why are they useful? Performance, power, and cost. So a whole lot more flops means you can solve your problem faster. So are many core processors new? No, they're not new. One of the first ones I was aware of was the stream processor work done here at Stanford by Bill Daly with the Imagine project, which was, I guess, over 10 years ago now. But really interesting project that really heavily influenced when the direction that NVIDIA and some of the GPU companies went in the direction of the evolution of graphics chips. So these were chips that a project that was developed for doing media processing with a particular style of computation, and also heavily influenced where the cell processor ended up. Sorry, let me just do a quick time check here. Okay, good. So what are flops useful for, right? So by flops, I mean floating point operations. Who cares about this stuff? A lot of the initial uses have been for gaming. So it's for doing physics in games, for doing the shader calculations in game, drawing the pictures on the screen. Image processing is another good example. So when you do photo editing on the Mac, some of the Mac software actually can use the GPU to offload brightness correction or contrast changes or histogramming of data. So there's a couple, that's sort of what's been leading the charges, these image processing and gaming applications. The other side of computing that has a use for all these flops is what's called high-performance computing or scientific computing. And so what I mean here is not the visualization side of scientific computing, but really these are sort of computational problems where an application is solving a big science problem, but computing the answer numerically. So these are typically math problems where there isn't a simple closed-form solution. I have to do some sort of iterative calculation or a PDF solver or something that is inherently a numerical calculation over a large number of steps. So where do people run these? Typically in large compute farms. So for large data set sizes, like oil and gas is a good example of this. So for an oil and gas company that has tons of seismic soundings of trying to figure out where oil is under the ground, they'll end up with terabytes and terabytes of data of seismic soundings they've done of the Earth. And they'll then run a calculation over a set of processors, anywhere from 1,000 to 100,000, to compute some value, right? Some answer of aim the drill head that way, go that way to find oil. And there's calculations like this in high-performance computing in a variety of industries. So on the server side, good examples are seismic processing, financial calculations in Wall Street. So Wall Street firms will have thousands of machines in New York or New Jersey for computing derivatives prices. It turns out stock options and bonds and whatnot have prices that are best determined using non-closed forms means. So they use these iterative numerical methods to figure out the correct values of the securities. So a lot of these applications are server applications, but there are some workstation and embedded ones as well. Embedded is typically medical ones for medical devices. So a CAT scan machine, for example, has quite a bit of processing to do on the data it acquires before it can display it. And then also these also appear in workstations. So a good example of this is sort of visualization stations that may be looking at seismic data, but also recomputing analysis based on the interaction with an expert user. So HPC uses computation to solve a science problem. So oil and gas, finance, biology is another one. Sequence matching is a good example of this, and one of the first problems that Brook tackled in the system that Stanford did, where they were doing protein sequence matching problems. Oops, I got a typo there. But in engineering, fluid dynamics is a good example too. So for aircraft design, they'll want to, before they build a plane and stick it in an air tunnel and spend a lot of money, they'll do a simulation on a computer to test different wing shapes to figure out which one is more efficient before they go manufacture a physical device. And then there's quite a bit of high-performance computing in government labs. So everything from nuclear stockpile simulation, figuring out what happens to warheads over time, how do they deteriorate, are they safe, to things like climate modeling. So who are the developers? These are mostly scientists, but they're not computer scientists. So if you look at folks who do this stuff, many graduate from Stanford every year, but they don't typically graduate from the computer science department. Even though they're going to go spend their living writing computer code, they tend to graduate from an engineering department or a petroleum studies department or a could even be MBA kind of program for financial modeling. For the sort of government lab stuff, it's often people with an applied physics background, numerical physics computing. So what's interesting about this for us is, and where we saw an opportunity here, is these are folks who are not parallel programming experts, right? Unlike a lot of people in this room, these aren't experts at really fancy computer science algorithms, creating threads, doing synchronization, doing communication across a network. They're really scientists, right? Their language is matrices. So for many of them, their favorite language is MATLAB. So they're more interested in their science and crafting it as a math problem and hitting enter and getting the answer than they are in optimizing a computer program. So pretty alien to me and to probably many people in this room, but they're really not programmers with the same depth of knowledge about optimizing a computer system that you and I have. So for those folks, multi-core CPUs and GPUs are a real pain, right? This is not something they like to do, is program big parallel machines. So they know how to cast their problem as a matrix problem. What they don't necessarily know is how do I make that run fast on a 128 core GPU or an 8-core process CPU. And developing threaded applications is hard, right? If you're an expert at it, if you've got the CS background, it's doable. It's pretty challenging for many people, though. So writing message patching applications is even harder, right? So writing a simple problem where I do an identical calculation on 1,000 machines is moderately difficult. Now when I have to do a calculation where those nodes have to communicate with each other during the problem in flight, that's now very difficult to code. And the sad part here is the trend in academia is actually away from teaching this stuff. So if you look 20 years ago, people were learning parallel Fortran dialects, and people doing scientific computing often were graduating with competence in those languages, things like co-array Fortran and even Fortran 90. The trend recently has been very much away from that, right? MATLAB has emerged, and MATLAB is really a pretty low performance language, right? It's a language where you easily get 1/10 of the performance of the machine, or much less. So the trend is actually against us here, right? So many people would say, oh, don't worry about it, people will get better at programming. Well, it's not really the way that things seem to be going. So that was the world we kind of stepped into at PeakStream. And sort of how do you connect these two things? How do you connect these scientists who have a very complicated problem to solve that has to run very optimally on the machine with these processors that are getting increasingly complicated, right? Adding multi-core into this mix makes it much more difficult than it used to be. So what we did is came up with a different programming model. We basically said, look, these guys aren't going to learn to do threaded programming. So let's come up with a different way that they can program where they don't need to write a separate program for every thread in the machine. So what we used was what's called a data parallel programming model. So this is a model that's been around since the dawn of computing with languages like APL. But in a sense, it's a much more matrix-like way to express your calculation. So it's a programming model where you work with large parallel arrays of data and describe transformations on large arrays. So it actually looks very similar to MATLAB. The magic of what we created, the technology, what was hard was making this run fast. It's easy to take something that looks sort of like MATLAB and say that's a statement of my problem. The challenge is how do you make it run fast on the machine and on a multi-core machine, a machine that needs threaded code running at its lowest level. So the way we did that is we did it with a compiler. So I'll talk about how that compiler worked. The other thing that was desirable about this, once we sort of come up with this basic architecture, is we could also make it portable. So we could insulate the developer from having to know whether they're running on a GPU, whether they're running on a multi-core Intel machine or a multi-core AMD machine. They could write it once, and we provided an abstraction that would mean they wouldn't even need to recompile to go to a new piece of hardware. And the way we thought about the problem was really two-sided. I mean, we clearly have to run efficiently on the machine, but we also wanted to make sure that it was a highly productive way to code. So I'll show you some code samples today. And I think you'll understand why we were so excited about this. So this is the first kind of very high-level software picture of how this worked. So we made some very interesting design choices here. I'll talk about it in a couple slides. But let me first, if you'll bear with me, just kind of rocket through this and show the high-level picture of how the system worked. So at the top, we have a high-performance computing application written in, let's just say, C++, right? C or C++. And that application makes calls to our system through an API. You know, we had a choice here between, do we invent a new language of some sort? Since we're going to create a compiler, do we create a language? Do we use an API? We decided to use an API, and I'll talk about how that worked, how the mechanics of that worked. But it turns out most things you can do with languages you can do with APIs. So we chose the API route because it was easier for people to use. At the heart of it is this PeakStream virtual machine. So under the API, this is where our compiler lived. So in the heart of the virtual machine is a JIT compiler, right? So this architecture picture looks very, similar to Java VM in some ways, right? So a lot of all the work we're doing is actually at runtime. So all the compilation work that I'll be talking about, something we're doing at runtime in the same way that Java does. So since we're doing this as an API, it's all just standard C and C++. So this made it really easy on developers, right? We don't have to go out and teach people Java or teach people some weird APL dialect. We just say use C++, here's an API, it's got a header file, there you go. That ended up being a really good choice for us. And then the last point, it just runs on standard stuff. So we didn't do there was no hardware aspect to what we did at all. You could just get a standard server with a multi-core CPU in it, or a workstation with a GPU in it and run on it. So there was no hardware aspect to what we did. We're doing good. Okay, so let me just jump right into code here, and then I'll back up and talk a little bit more about why we made some of these design choices and how they worked out. So this is what code looked like in this system. Is that readable in the back? Somewhat readable? Okay. Okay, so the basic data type in the system is arrays. So if you've ever looked at MATLAB or APL, this looks remarkably similar. So the basic data type is arrays. Array F32 means floating point 32-bit, so single precision floating point. So this says I want an array of floating point values. Could be anywhere from 1 element to, I think it was 4 million we did in the first release of our software. So you basically make a big array of data and then describe transformations on that array. So we create some arrays. This make call is sort of saying take a normal array and turn it into one of these arrays so I can do calculations on it. And then in C++, we just use operator overloading to describe calculations. So if I want to take two arrays and add them or subtract them, I just take the arrays and add them or subtract them together. There are rules. They need to be the same size, the same dimensionality, stuff like that. But it just sort of does the obvious thing. It does the element-wise calculation on all the elements of the array. The same way it would in MATLAB. And keep in mind, we're trying to appeal to a MATLAB community. So this was a neat property. So the other thing we did is added a bunch of intrinsics functions, which really just means a library, right? So what about a matrix multiply? There's no built-in language thing for that in C++. So we just have a library function called matmul. So you say, take this matrix, multiply it by this vector, and it does the right thing. Keep in mind, this is for solving very large matrix equations. So typically, users would have a 1,000 by 1,000 matrix multiplied by a 1,000 long vector. So very big arrays. Or dot products, et cetera. So basically, in most cases, we were actually able to use the same function names as in MATLAB or Fortran. So for our community, this is a really nice property. If they're used to writing matmul, they can just write matmul. And then after you've done a chain of calculations, so we're doing a chain of calculations, we're even doing loops and stuff like that, we tell the system we want to compute a whole bunch of stuff, and then at the end we read it back. So we make a call and say, give me my data back, put it back in the CPU memory. So in a second I'll get into talking about some of these design choices, sort of why did we do it this way. I think that's one of the problem that Eileen was interested in, is sort of for the Stanford community, why would you design it this way? Why is this the right way to do it? So any questions at this point? Yep.
So in the video you were talking, you mentioned that today's scientists are more likely to be a MATLAB user rather than a C++ or Java user. Yeah. So why you still choose to develop APIs for standard C and C++
That's a good question.
Integrating into MATLAB?
Yeah, let me repeat the question for people out there. So the question was, if your users know MATLAB, why didn't you do MATLAB? Why do C++? That seems like an odd language choice. Yeah, I think that's a reasonable point. We were certainly looking at doing MATLAB, and I think given infinite resources, would have. What we found is people often prototyped in MATLAB, but then they coded their final version in C++, and so that told us. So our fear was MATLAB couldn't get there, basically. Because MATLAB is inherently not a high-performance system that we just couldn't get where we needed to get. But it was a somewhat imperfect answer. It's a good point. In an ideal world, we would have just said MATLAB is fast, but we didn't think it was feasible. Good question. OK, cool. OK, so why an API? This is a question we get a lot. Why didn't you just invent a language? The basic answer is because inventing a language is really a nightmare for users, right? I mean, it's really fun to invent languages, and I like inventing languages. And for a paper I was writing about a new idea, I would invent a language. But they're very hard to learn. It's very hard to develop the tool sets you need around a language. When you invent a language, you need a new debugger. You need a new profiler, or at least you need to seriously extend the ones that you had. And you got to go teach people to program the language, right? There's no books on your language, so you got to go make books on your language. You got to teach courses at your language. You have to get university courses in your language. So for a startup company, this is you just can't do it, right? Startup companies need to start making money and have some plan to do some sort of acquisition or IPO within, say, 10 years. You just can't do that with a language, right? Look at Java, right? Java took 10 years to really take off, and so. I'm a big fan of languages, but it's difficult to do in a startup context. The other comment I would make is we got remarkably far with APIs. And this was an insight of Pat Hanrahan's, actually. I give Pat full credit for that. As Pat, very early on in the company, really said forcefully, these are really the same. APIs and languages are equally expressive. And if you look at it in the right light, that is true. There are some things that are more elegant in languages, but there's really not a difference in expressiveness in what you can do in the two. So given those realities, APIs seem like the logical choice for us. They're much easier for users to adopt. You can cast them in language-neutral ways with different language bindings for different languages. And they facilitate interoperability with existing software. One bummer about creating a new language is now you have no libraries for your language, right? So a nice part about using C++ is you can just say, I integrate with other stuff. If there's a networking package I like, or MPI, or whatever, it still just works. So another interesting design choice we made, the technology that made this possible was doing a virtual machine, right? So when you talk about doing an API, our system needed to run efficiently, our system needed to do significant optimizations, loop optimizations, loop unrolling, loop peeling. So we needed to create a compiler. The choice we made was to do that at runtime with a dynamic compiler embedded inside a virtual machine. That has some nice properties that we didn't seek to have at the beginning, but were neat, freebies. One of them is binary portability, right? In the same way that you can take a Java application that's in Java bytecode and just take it, move it somewhere, and it runs on a Mac, it runs on Windows, it runs on Linux. We didn't have quite that level of portability, but we had portability in that we could change the underlying processor, right? We could add a GPU to the system, and we wouldn't need to recompile the app, which is a neat property. So we could dynamically compile and optimize for the processor at hand. So what would happen is, as you started making API calls, first thing it would do is start up the VM, look at your hardware, and say, what do you have in this system? Oh, I'll use the GPU. Oh, that's a bad GPU. I'll use the CPU. Oh, look, dual Clover Towns. That's great. I'll use the CPUs on this one. So that was why we made the choice, and it worked out very well. It also meant we could bridge this gap between GPUs and CPUs. Some people wanted to use GPUs, some wanted to use multi-core CPUs. It allowed us to present an API in a way to program where you could build an executable and then change your choices about those and support a bunch of different processor types. And then another observation is that I don't think this would necessarily work in all fields, but in high-performance computing, dynamic compilation tends to work very well. And the reason is because the data sets are huge, And the code tends to not be that large, right? You're operating on the same data over and over and over again. If you look at seismic processing, it has that characteristic, and a lot of high-performance computing tasks have that characteristic. They load a large data set, they do a large number of iterative computations on it. I'll get to you in just one sec. So the result is, even though compilation is not cheap, right? We might spend 10 seconds to compile the first time you do something hard. You're probably going to run this thing for 4 hours, so 10 seconds doesn't matter if you're looking at a 4-hour run. Yes, question?
Presumably thrown out a lot of semantic information that may have been present in the original source code when you went through your intermediate bytecode. Does that mean that the quality of the code you're compiling is significantly lower, or are you able to recover that through profiling or something else?
That's a great question. So for people on the SITN, the question was, if you're doing a JIT, if you're figuring this stuff out at runtime, you've lost a bunch of semantic information. How do you get that back, or is it just lost, or what does that mean for your system? That's a great question. You do lose a lot of information, and so a lot of it we get back through heuristics in the runtime system. So probably the worst semantic information we lose is loops, right? We don't actually know where the loops are. So if we look at this code here, right, we've got a loop here executed on the CPU. We're getting these calls. We're just seeing matmul calls and dot product calls come in. And what we do is actually we'll infer that there's a loop going on there. And it turns out that's actually not that hard to do. We do just sort of standard heuristic tricks, which is, things like look at the stack, look at the caller, figure out, oh, this is the same PC. Boy, this looks like a loop. So we can't, we have to view that as a hint, not an assertion, right? It's not a directive, but we can use it as a hint that there's an optimization we may be able to apply here. And so that was our approach. So we found with heuristics, and we were able to get quite far. But it is true you've lost quite a bit. The place it hurts is if you don't have large data sets. So if you have large data sets, this isn't a huge problem. If you start wanting to operate on arrays with 100 elements in them, this is a huge problem. You really need to know where the loops are. You don't have time to go do these heuristics. So it doesn't work for everything, but it works for large data set HPC problems. Yeah, great question. Yeah, and I guess the other point I would make is dynamic compilation has gotten a lot faster than it used to be. So I think VMware does phenomenal things with dynamic compilation, manages to boot, actually boot Windows or Linux in a VM in an incredibly quick time. At the end of the day, it looks just as fast as running on your hardware. So the technology for JITs has gotten a lot better. So we're really able to benefit from that. But really, for HPC, two things that really helped us is the data sets are huge, and the code is reused over and over again in loops. So code caching is very effective and keeps our compile time down. We're just not compiling that much. And these applications tend to run for hours, so spending 30 seconds JITting is really not a big deal. So let me show another example. I want to give you some intuition for what the VM actually does. So let me show a concrete example. So this is a silly little program I wrote very early in the company history to compute pi. So this is actually an awful way to compute pi. But if you want a simple teaching tool, it works pretty well. So the idea is to draw a square.
You can ask for the overhead camera.
Oh, is that? Oh, I can just do it here, right? Cool. Can I do the overhead camera here? Great. OK, so right, take a piece of paper, draw a square, inscribe a circle in the square, and now throw darts. I can't draw a very good circle, but now throw darts at this thing, right? Not a very good method, but if I do this a lot, right, if I do 1,000,000 darts, let's jump back to my slide. And I figure out what's the ratio, what percentage of the darts landed inside the circle, right, which turns out to be easy. I just figure out whether their distance from the origin is less than 1, then they're inside the circle. If I do that, figure out that ratio, it turns out if I multiply that by 4, that's an approximation of pi. It's not a good method because you have to throw a phenomenal number of darts to get any sort of accuracy, but it's simple and nice. So how do you code this in PeakStream? Well, first off, you throw a lot of darts, right? So we declare a constant here, n set, which we'll set to 1,000,000 or something, and then we call our random number generator 2 times to make arrays with 1,000,000 random numbers in them, right? So this is an array-oriented system. You're constantly making massive arrays and treating them like they're free. It seems like an odd way to program, but this is the same way you would do it in MATLAB. So it may seem odd to you and me, who are, people are used to writing loops in declarative imperative languages like C++, but in MATLAB, this is how you code. You tend to create large arrays. You then calculate for those points in a data parallel way how far they are from the origin, what's their distance from 0. We figure out which ones are inside the circle, which one whose distance from 0 is smaller than or equal to 0. That gives us a million element long Boolean vector. And then we add that up, divide by the number of trials, multiply by 4, and we have an approximation to pi. So this is what I was alluding to earlier. I mean, for us, this is an exciting picture. This may seem like a silly example, but what's neat here is we've done a fairly complicated example in a handful of lines of code, and it looks very similar to how you could code it in MATLAB. So what does the compiler do? How does it actually run that code, right? We've written that weird stuff. How does that run on Multicore, right? That's what I said the VM does, but I haven't told you anything about how it actually does that. So what we do is generate a series of compute kernels, and we're drawing on an idea here. Compute kernels are a term that Bill Daly came up with the Imagine work, and it's a neat idea. The idea is that since these processors have a high floating point to memory access ratio, let me rephrase that. The processor is horrible at doing memory traffic, right? So the goal in optimization on a modern processor should be to read and write as few things to memory as possible and do as much floating point as possible, right? Which is an odd statement, because when I went to college, we were taught to do as little floating point as possible. But the world has changed, right? Floating point's free. What's expensive is reading and writing memory. So what our compiler does is that's its optimization principle. It's not trying to minimize flops. It's trying to minimize memory traffic. So what it does is looks at your program, does a very high-level optimization pass on it, where it tries to figure out what's the minimum number of compute kernels that I can execute, because a minimum number of kernels means a minimum number of reads and writes to memory. Another way to say that is we're trying to maximize flops per kernel, right? So doing a kernel means reads and writes to memory, so I want to do as few as possible to avoid doing memory traffic, because that's what makes your code slow. And we do all that automatically. So to draw a picture of it, this is what we're really saying, is we take your program, we look at all your calculations where you're adding arrays up and doing random number calculations and stuff, and we take your program and smush big chunks of it into one kernel and smush other big chunks of it into another kernel. Kayvon used to say this thing, which I kind of like, which is, it's like we're taking your program that you wrote one way and we're sort of slicing it the other way, right? We're pretty radically restructuring your program in order to eliminate memory traffic. Yep?
Are you trying to explicitly eliminate memory traffic on and off the chip? So you're not going to run kernel 1 and kernel 2 on different processors and just go on chip between the two of them to eliminate that traffic?
It's even a stronger statement than that. So if we look at the code here, what we're trying to do is make it so that when we compute something, we use it right away and then never save it to memory. So if you look at the calculation here, the way it's expressed, it looks like we write the array x out to memory. But what we do is we never write x out to memory, right? We look at this program and realize, well, I only need x so that I can square it and add it to y, so I should never write it out to memory, right? So what we're doing is taking this program that would appear to do a lot of memory traffic, and we're figuring out how to sort of slice it into these vertical chunks where that memory traffic will just be in register and will never have to go out to actual RAM.
But between kernels, do you always go to and from main memory, or do you ever have two kernels run?
We always go to and from main memory between kernels. I mean, it may actually be in the cache, but it's at least, even the cache is expensive these days. So what we're trying to do is keep things in register and maximize the amount of compute we can do with everything in register. Yeah, it's a good question. So what do we do? So I'm talking about kernels. What does this actually mean? Well, remember my Pi program, right? It was like 5 lines of code. This is the series of passes that we come up with to compute Pi. So this is what our VM generates and then causes to be executed. So you just make these calls into an API. Under the hood, we look at your calls and say, no, you're doing it all wrong. That all looks like memory traffic. And then we turn it into those compute kernels and say, OK, we can actually do it this way. And so, for example, when I talked before about how the X array never gets out to memory, what that means is that in pass 1, we generate some X data, but we never actually write it out, right? It's fully consumed in here, and we'll do a write at the very end. So on a GPU, this I think was the, which one was this? This was the R580 GPU from ATI before they got by AMD. But so this is a GPU executing this code. It turns out this is a 6-pass algorithm. So we'll do one kernel that does the random number generation and most of the flops. So almost all the flops turn out to be in this kernel. And then we do a series of kernels to add up all the values. It turns out on the early generation GPUs, adding up all the values is tremendously difficult. So there's a bunch of passes you have to do that. And then there's one final pass where we basically divide by 1,000,000 and multiply by 4. So that one's really simple. Yeah?
So each of these passes here is a separate kernel which is going to gather and then scatter the data back?
Yes. In most cases, it's not actually gathering and scattering. They're just writing and reading. It's not always shuffling memory. Right.
I guess my question is, why, if you have 6 processors, why not run one instance of each of these and just avoid going out to
okay, so the question was, if you have 6 processors, why not just have each one run this? Well, in this case, 90% of the flops are in this first kernel. So the problem is if you do that, it will load balance horribly. What you're describing is pipelining across processors. And if all the work chunks are the same size, that's a great approach. But in this case, they're not. So it doesn't work well. So that's the heart of what we built. And that was actually the hardest technical problem on the compiler side, is this automatic stream kernel synthesis. This idea that, and that's where we also differed a lot from the Brook project. Brook made this the developer's responsibility. Brook had a notion of kernels, but when you coded in Brook, you had to decide where the kernel boundaries are. And at PeakStream, we took a different approach and said, our developers can't figure that out. And it's different for every processor, so we didn't think they should figure it out. So our approach was to say, we'll just have them describe the calculation, and we'll figure out how to break it up into kernels. And it's a good task for compilers. We were actually very good at it. We often found that the compiler would do better than we could do by hand. Not always, you'd find bugs, but it's neat. You can tell your compiler is doing well when it thinks of stuff you don't think of. We often saw that with constant folding. That was the thing that's sort of hard to always do in your head rigorously that it was very good at. This is a picture of how it actually worked inside. So what is it? So this application binary at the top calling into an API. This is the heart of it. So the JIT is here. I've talked a bit about what this is doing. So this is looking at, is deciding what the kernels are going to be. There's quite a bit of software here that has nothing to do with the compiler. So we actually spent quite a bit of effort on more systems level components, things that we're deciding what's the order in which we're going to run the kernels, right? Once we've generated this DAG of kernels to be run, how do we decide what's the optimal order to run them in to preserve locality and things like that in the memories? There's quite a bit of memory management that we have to do. So we're completely hiding the GPU or multi-core memory from the user, right? The user doesn't have to think about what fits in cache and what fits in physical memories. We make it work. So there's quite a bit of work we had to do around making it that easy. And then the executor, this piece at the bottom, is what's responsible for actually managing the processor. So on a GPU, this means feeding commands over a command FIFO to a GPU and getting data back asynchronously and all this graphics stuff. Even for multi-core, the executor has a lot to do. It's got to start up all the threads to run on the multiple cores. If you're running on a dual socket 4-core system, it's got to get all those threads running. It's got to make sure they're load balanced properly. And this is all stuff that you as the developer don't have to do, right? You just call the APIs. You don't have to worry about threads. So this is something people often don't realize. This stuff is actually equally hard. The compiler stuff is sort of the nifty stuff that sounds like the neatest algorithms, but this is actually a pretty interesting problem too. It's just building the whole runtime side of the system. It especially got difficult because we wanted a debugger and a profiler, and I'll show you what those look like. But they put major strains on the rest of the system because they want it to do really annoying things, like look at data that may never be in a memory, right? So we may have an array X that never gets written to a memory, and yet the user wants to look at it in a debugger. How do we do that? That's hard. So this is kind of a laundry list of what's in it. So it's let me skip over this because we're a little short on time, but you've got the slides. I won't go through these in detail, but I want to show you a couple other real-world examples, like what do codes look like. So here's a Mandelbrot fractal. Not something anyone would run in production, but we've probably all written a fractal code at some point, so we've all seen this. So this is doing a bunch of calculations on a large data set. I mean, what's neat here is, just how simple this is, right? It's a bunch of code, but Mandelbrot calculation is simple. It should look simple at the end of the day. And that's a lot of how we would evaluate ports on our own, right? If it didn't look simple, we'd think about how do we change the API to make it simpler. So we did a lot of work on debuggers and profilers. Let me just show you. The Linux versions are kind of boring because they're just text-based. The Windows versions are more fun because we wrapped GUIs around them. So on the debugger side, what we did is integrated it into Visual Studio. So in Visual Studio, you could basically get a little view of what are my, on the stack, what are the arrays that I have on the stack. And if you clicked on an array, you could just see the array pop up here. Let me see if I have. You could also do sort of graphs of that stuff. So looking at a huge sea of a million numbers isn't a lot of fun. So we could also come up with color-coded, show me the nans in red and the, show me a ramp of values of the 0 to 1 values. What's interesting here, let me just see if I have a slide on this. Yeah, it turns out this is actually quite difficult to get to work because, as I said, the array you want to look at may not be something we were ever going to write to memory. So we actually have to reach fairly far into the virtual machine to tell it to compute things that it may not otherwise have computed, right? So that's why there's some sort of subtle system aspects that are much harder than they look at first glance. We also did a profiler. So we did, again, this is integrated in Visual Studio on Windows, so you could get views of these are the calls that I made, how much time are they spending on compute, doing flops, how much memory traffic are they doing, et cetera. You could even see, am I paging the GPU memory, am I paging the Clovertown memory? So we did quite a bit of work on tools. At the end of the day, this wasn't a tremendous amount of labor, but it was a lot of design. So it was challenging, but I think it was really important. So these are some benchmarks we did at the time. These are a little stale now because processors have changed since we published these. But what we're showing here is this was an oil and gas application for seismic migration code running on a GPU with our system versus running on a traditional dual-core CPU at the time. And the one on the right is showing a Monte Carlo finance simulation. So this is doing an options pricing calculation. And the codes are in the slides if you want to look at them. We're a little short on time, so I think I will just blast through this bit. So this is the Kirchhoff seismic migration code. And again, what we're psyched about here is here's a code that people run in various forms in production 24 hours a day on huge server clusters. We can express it in 20 lines of code. So the real ones people run are a little more complicated than this, but I think it's important that the core algorithms be simple to express. This is the options pricing code, and I'll leave you to look at those on your own if you're interested. They are in the slides on the web. So I'll open it up to questions in just a minute. I've just got 3 slides more that I thought would be interesting to talk about with this group. Yep. Okay. Oh, maybe my watch is a little fast there. Okay, good. Good. So let me talk a bit about hardware and where I think that's going, and then talk a bit about software and where that's going. Sort of what did we learn from our experience building software for these things? Where do I think that's going in the future? And then I'll conclude and open it up to questions. So, so first off, on the hardware side, it's been a very interesting few years in the last 5 years, right? I think 5 years ago, GPUs were not programmable. None of this stuff, the genie wasn't really out of the bottle yet. I think it's had a very interesting disruptive effect. I think it's starting to become clear sort of where this is going. It wasn't obvious 5 years ago, but it's getting more obvious to me. So I'll tell you where I think it's going based on some of the things we're hearing in the industry, and I would love questions and comments at the end too about your thoughts on that. I think the direction this is going long term is towards integrated CPUs and GPUs. So as GPUs have become programmable and CPUs have become arguably more GPU-like with things like the cell processor, which is somewhere in between the two in system architecture, they seem to be converging to some common place in the future. And so the dominant processor vendors have started talking about this some publicly. So I guess I'd refer you to that. One is AMD's Fusion project, which there's been some discussion and announcements from them on the web about, and then Intel's Larrabee project are both interesting moves in that direction. And I think that's where we're going to end up in 5 years. is I think this period in history now where we have dramatically different CPUs and GPUs, I think is going to be short-lived. Because GPU, so the thing that started to make this obvious to me was the fact that GPUs and cell processor are really not that different, right? When I first saw the architecture diagrams for the cell processor, my initial reaction was that looks just like NV40, right? It looks just like some of the GPUs that we've built. So in a practical sense, the architectures are the same, right? They're remarkably similar in terms of how they're being built. There's some subtle distinctions in terms of how communications work or whether they're cache coherent or things like that. But there are a lot more similarities than differences. So I think the direction we're going in the next 5 years is towards chips, single chips that have sort of on one side of the chip a control processor or 2 control processors or 4 control processors. But on the other side of the chip, something more like a traditional GPU. So some sort of compute array. So in a GPU, this may be 128 processors for doing shading calculations. On the cell processor, these are the SPUs, right? I mean, cell is an example of this kind of processor today. On one side, we have a PowerPC traditional core, and on the other half, we have this sort of dense array of connected, simpler processors. You know, and these things are being developed. What's surprising is these are being developed for gaming, right? That's actually the driving economic force that's causing these things to come into being. What's interesting for the rest of us who also do other stuff is it's also a great processor for doing high-performance computing, for doing any sort of numerical computing. So it's kind of interesting. I don't think any of us would have predicted that gaming would be the killer application that would cause a great high-performance computing processor to be created 20 years ago. So where is the software going? What have we learned from what we did at PeakStream? I think one is, I think there's a recognition that we need new programming models, right? I mean, the threaded model has been here for a while. On the face of it, threaded programming seems to be a fine answer for x86 multicore. But as we've talked about here today, there's a lot of users who don't know that programming model or aren't proficient with that programming model. It's not working for people, right? There are a lot of real-world application codes that when you run them today on multi-core processors don't run appreciably faster than without multi-core processors. So I think there's room here for new programming models, which is good news for academia, right? You guys are in the right place. This is a good time to be thinking about new programming models. So data parallel is the approach we did at PeakStream, and that's one approach. I think there's a lot further that data parallel can go. But there are other approaches, too, that are interesting. So I would encourage all of you in this room to think broadly about that. There is a space for new models to arise right now. So how do we expose new models? I hope I've convinced you today that languages are certainly one way to expose new models, but APIs are also a good way to do it. So if you're looking to mess around with this stuff, I'd encourage you to look at the API approach. It's got some very nice characteristics. It worked well for us. You know, the other side of it is I've seen in a bunch of systems increasing importance and reliance on runtime systems. You know, one of the first places I think many of us saw this was in Java, right? Java had this fully formed large runtime component that looks very similar to what I put on the board here, right? And here's another system that's got a pretty crazy optimizing compiler embedded in the runtime of a library, right? That's a pretty odd idea. But we're seeing more and more systems like that. One thing I've been observing recently is game engines are starting to become massive runtime systems. So also on the gaming side, we're starting to see that the runtime aspect of what the game is doing, significant computation is going on at runtime. So one is compiling shaders for GPUs, but it's even getting more sophisticated than that as people are starting to do more sophisticated physics inside computer games. So if you're interested in compilers, I would encourage you to think about their application inside runtime systems. VMware is also a great example of that. Here's another company where compilers are at the heart of what makes those VMs work. So that's interesting, right? It's sort of reinvigorating the compiler community, I think. And this is you know, I think it's good for those of us interested in compilers. As these processors are evolving and changing dramatically in the next couple of years, there's a lot of work to do to make systems run efficiently on them. And what I like about runtime systems is they do it in a way where you don't have to recompile the application code. So anyway, last slide, and then I'll open it up to questions. I think that the pitch I'd like to make to you is the world needs good programming environments to make parallel programming easier. There's a lot of work to be done in this field, and I hope you will do it in the research arena, and some of you will do it in the industrial arena. I think this need is going to be around for a while. So PeakStream was one such solution, data parallel programming model for programming Manycore systems. But very curious what the rest of you have, what thoughts the rest of you have on that. So thank you very much. Okay, I'll open it up to questions.
Before you were acquired by Google, can you talk a little bit about how this product was received? Was there enough time there?
Yeah, I can't say a tremendous amount because Google hasn't announced anything about specific intentions with regard to the product. So I can't say a tremendous amount there. I mean, I think there was a tremendous amount of press and interest by customers, but I can't sort of put numbers to that. Yep.
Is anyone using this to program the PS3?
Is anyone using this to program the PS3? We didn't support the PS3. We didn't port it to that, so no one's using our software to program the PS3. Is anyone using an approach like this? I don't know. Yeah, I'm not really that close to that world. I think certainly Kayvon's work, Kayvon and Pat have done some work on this system called Sequoia, which they were looking at cell processor as a target for that. And I would refer you to the Sequoia work. There's some very interesting papers on that, and they thought more deeply, I think, about cell than we had a chance to. Yep.
Do you see any need to change how this works if you envision 5 years from now where I've got 1,000 x86 processors on a chip with 10 times the memory bandwidth? So it's gotten even worse in terms of going off chip for memory.
Yeah, so the question was, how would this change if you had 1,000 cores on chip? And now getting memory is relatively even more expensive. Yes, I agree. I think this system would start to be taxed by that. I mean, we were looking forward to systems like that, but you can only look so far. I think we should all be thinking about that problem. How are we going to program a 1,000 core system, right? There's not a good answer to that question. So I think this is one approach. There may be other approaches too, but I think we should all be thinking about that because programming that by hand is crazy.
And a follow-up to that,
Yep.
Did any of the applications that you looked at in this context have sufficient computation per memory access that they'd actually make any use of a 1,000 core system? Or do we just not know how to write software that can even use something unless we magically solve the memory bandwidth?
So the question was, did any of the apps we looked at, could they actually use 1,000 cores? Yeah, I would change your question. It's the answer is yes, they could easily use 1,000 cores. And the proof of that is that they're running on systems with 10,000 machines in them, each with multiple cores. The more damning answer, though, is that we can't use all the flops. So chips have too many flops, which is a bizarre statement, but it's true. All right? We can put more floating point on a chip than we can feed with memory. So that's actually, I think, the symptom. And I don't know what the answer to that is. I know you have to do things like this to get good performance, but at the end of the day, you tend to find you still have more flops than you can do anything with. Yes? Question?
You provide some advice to hardware vendors to improve the ability of multiple cores to cooperate together. What would it be?
So if I had advice for hardware vendors to improve the ability of the cores to cooperate together, that's a good one. That's a good question, to which I don't have a simple answer. On-chip communication mechanisms are really important. So personally, I'm a fan of shared memory as a way to describe transfer on chip. But I think you need to be transparent in telling developers what's efficient and what's not efficient, right? Shared memory provides this illusion that everything's free, but it's not free. So you really need to pretty deeply disclose to software vendors how it actually works. What's the snooping protocol? Which processors are close to which processors? You know, that said, most developers aren't going to have any idea what to do with that information, which is why I think we should be using compilers to encode that knowledge, because mortals can't use that stuff. But a compiler can use it very well. Yep?
So what is the prospect of using this system for web serving applications like PHP, .NET?
The question is, what's the prospect for using this for PHP?
Separating for web analytics.
For analytics. I think this is a lot more applicable to analytics than to PHP serving. Yeah, I mean PHP serving is just latency sensitive. Not so. The way I think about it is to borrow some words from Intel. This kind of approach is very good at high throughput, numerically intensive computing. It's not good at low latency, small amounts of data kind of stuff. You need big data, and so analytics have that character. Yep.
All the examples you show basically a set of primitives which look like an awful lot like the primitives of MATLAB, but you're basically invoking them at a high level. Can the user add new primitives, or are they basically stuck with the set you provide them? Yeah, the question was, can the user add new primitives, or am I stuck with the set you provide? In the releases we shipped, you could just use the ones that we provided. So we did have general scatter and gather tech. So the place that would hurt the most tended to be communication, right? How do I reshuffle data to do some calculation with it? So the way we answered that was by having general scatter-gather mechanisms so that I could reshuffle memory. But that is something that we were very interested in doing in the future, is looking at how you provide extensibility, and I think it's very important. But if I need to execute some arbitrary function of my own on each element of an array 32, there's no way to push that out to the GPU.
Well, at the end of the day, the GPU runs C code, right? A restricted set of C. So in theory, if you look at how our VM works internally, we just had a table of these are the intrinsics we have, and we have rules about which ones can be patched together and which ones can't be patched together. In theory, there's no reason you couldn't open that to the user and say, here's how you can add your own functions, and our compiler can reason about them. So I think it can be done. We didn't get that done.
Right, but that's a limitation of the API approach. You can't get that from the C code, the C++ code that the user has written.
You can't. I think you can do that, but yeah, it's not. Yeah, that would be an interesting thing to talk about afterwards. I do have some thoughts in that direction. I think it can be done. It does get a little tricky. That's more elegant in languages. I certainly agree with that. Yes, in the back.
How did you go between using memory locally attached to the GPU and the memory mapped into the system? How did you allocate your data structures to be in local memories attached to GPUs?
So the question is, how do we manage memory that's in the GPU on the GPU board versus system memory that's on the motherboard? The answer is it was all magic, right? Like MATLAB, we basically said memory's not your problem. We're going to handle all the memory. So we entirely hid it from the application, which meant we had to do a lot of memory management. So we had LRU caches for what's in the GPU memory, but also caches for, well, system memory always fit. We were not paging system memory in the version that we shipped. But, so the answer is we were hiding it all, which seemed to work pretty well.
When you ported to different processors, you had to
Yep. Yep, you might have to do it different. Well, and the number of levels of memory hierarchy would be different on when we did a port for x86 for dual socket Cloverton systems. You didn't have a separate GPU memory, so a whole layer sort of went away in our memory allocator. Yes, question in the back.
How do you see your technology intersecting with sort of the virtualization wave that's going on?
That's a good question. So the question is, how did I see this technology intersection with the virtualization wave that went on? I don't know. That's something we thought about a lot. I don't have an easy answer to that. I think there may be some opportunity there. I don't know the answer though. I think something may emerge in the next 5 years. Maybe we'll figure it out in this room. But I think that is an interesting question: is what approach should we take to these big parallel machines? Should we divide them up between different workloads? Do I have enough workloads that's viable? I think there will always be jobs that want the whole machine, but there's some balance between those two things. I don't know. Good question. Yes?
Did you have any provisions for explicitly managing data transfers between cores on a multi-core chip, or was it all through shared memory and you hoped it got cached appropriately?
That's a good question. Actually, Brian, do you want to field that one? Our Chief Compiler Architect Brian's in the back. I'll let him take that one. He was the expert at that.
The short answer is no. We didn't really take advantage of that. We did deal with some locality issues, particularly in some of the more complex numerical algorithms like matrix factorization. We took care to make sure that there was locality in the code that we wrote. And we actually did experiments on NUMA systems and examined locality issues there. We actually found that the most robust answer was just to interleave the pages across different demo banks. And that, so you could do slightly better, but not dramatically better, interestingly enough, by trying to manage the locality more. But it was far more robust to just,
and a whole lot
of
of
systems we were experimenting on. So.
Yes, question in the back.
What is the future roadmap looks like for the VLIWR?
What does the future roadmap for VLIW architectures look like? I don't know. That's a good question. I really haven't been in the VLIW world, so I'm not qualified to say. The processors we were doing were not really VLIW processors. They're don't really have that character. Yeah. So there may be some future thing in architecture there, but it's not something I've been tracking as much. Yep.
Along similar lines, I know that Larrabee, for example, has, I think it's 16-element SIMD or something as its major form of computation. Do you see extending what you're doing to both be parallelizing at the core level and parallelizing at the SIMD level, or you don't?
Oh yeah, that's a great question. You brought it up in the context of Larrabee, but it's an equally good question for dual socket quad core, right? Because those have SSE units that are four-way, and GPUs have four-way. Some of the GPUs have four-way SIMD units at their heart as well, with other cores layered on top of that. The answer is we did both. So our compiler would handle spreading work across the SIMD cores and across the physical cores in the chip, and we were able to do that quite well. That work, and in fact, in some ways, the fact that you have to do SIMD stuff when you program this stuff by hand is one of the biggest hassles, right? Because you sort of have to do this whole parallelization problem across cores, and then you have to do this parallelization problem across SIMD, which doesn't leverage any of the skills you learned in the first one, right? And one of the things I'm learning at Google is, at Google, we have to think about parallelization across the entire cluster, right? So we have a third axis that we have to think about. And this is one of the, I think that's the big problem that's sort of driving software people nuts right now, or at least me when I try to write very parallel high-performance codes, is there's three completely different kinds of parallelism I have to keep in my head, and somebody's probably going to invent another one in a couple of years, right? Well, I have to think about the cache, too, right? Completely different set of design trade-offs. So I think that's a really rich, interesting research area, is there some way to unify this stuff? Because it's just not for the faint of heart. I mean, I'm an expert at this, and I find it really hard to tune for all those things at the same time. Yep.
So let's let that be the last question for us. Great, and thank you, Matt, for kicking us off with the first week. It was a great talk.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.